Hi everyone. Welcome to the Verification Future Conference of Track 3 VHDL verification. So we have Epson here from the Emologic. Epson, can we start?
Yeah, sure. I'll just start.
Yeah, sure.
Okay, thanks. So my name is Espen Tallaksen. I'm going to talk about a pragmatic approach to improving your FPGA VHDL verification. I'm the CEO of Emologic, the design center for embedded systems and FPGA based in Norway. And I'm also the author and architect of UVVM, which I will talk about in this presentation. I've always had a strong interest in pragmatic methodology improvement, and UVM is really a result of that. So just before I start, I just want to say a few words about Emlogic. Let's see. So, as I said, it's an independent design center for embedded systems and FPGA in Norway. We were established only 3.5 years ago, but we had an extreme ramp up from just me to 44 persons now and 18 on FPGA. But we continue the legacy from a previous company that I was working for. We are a verification IP and methodology provider through UVVM. We also do courses, one course on FPGA design, another course on FPGA verification. You can just check our website and get more information on that. We do most courses online these days. So, what is UVVM? It's a universal VHDL verification methodology, which is a VHDL verification library and methodology for FPGA, ASIC, and CPLD. It's free and open source. And currently it's being used by 35 to 40% of all FPGA VHDL designers worldwide. It has a very structured infrastructure and architecture, but more important, it allows the users to make their test benches with a really good architecture. And that significantly improves the verification efficiency and ensures a far better design quality. It's recommended by Doulos for test bench architecture. We work with ESA, the European Space Agency, to extend the functionality. We have run 3 projects or 2 projects so far. It started the 3rd project now in March. And UVM is, of course, also running on NASA projects. It's available on the IEEE Standards Association open source project and also on GitHub. Most people would most probably fetch this from GitHub. And UVM runs on any VHDL 2008 compliant simulator. And we test it out with Questa, Model Sim, Revera Pro, GHDL, and NVC. So when we look at test benches in the industry, we see that the quality of these are far worse than for design. The architecture is normally far worse, resulting in a far worse structure, far less documentation, and far worse coded. And we tend to waste far more time on verification than we do on design. So when I look at different customers, different companies in Norway, in Europe, and worldwide, I would say there's a saving potentials from 20 to 75%, depending on the current situation in that company and how mature they actually are with respect to verification. And of course, 75% reduction means 4 times the possible time, which is not good. On average, maybe a factor of 2. And the test bench quality could have what I call double quality improvement, because the test bench in itself could be much better for finding bugs. And then you also have faster verification, allows more verification. So if you compare this to the design solution, how we do design for FPGA, we have the same issues for verification. We want to have overview readability, modifiability, maintainability, debuggability, and reusability. And you want to use the same approach. You want to have a basic infrastructure, divide and conquer at all stages, and prioritize the reader at all times. I'm not saying that all RTL designs are like that, but they should be like that. We should have the same solution. We should really focus on architecture and have a simplicity where it's needed the most, because not everything can be that simple. We also have the same challenges, in my opinion, and that is awareness. People have to be more aware that there is a huge improvement potential, both on design and verification. So this is an overview of the UVVM system, and I'm going to go through the different parts of UVVM. I'll start by looking at the utility library and the bus functional models. So for that, I have an example of a test sequencer code, and I'm also going to show the transcript and log for that. So the device on the test here is a dead simple interrupts controller. It has a clock and a reset. It has a simple bus interface, which is just a processor interface to access the internal registers, and different interrupt sources, and a resulting interrupt to the CPU. This is a dead simple module. When you want to make a test bench for that device in the test, the first thing we need is, of course, a clock generator. And in UVVM, there are plenty of clock generators available. They are available as procedures in the UVVM library. And this is just showing the simplest of these procedures. So you have other ones with far more parameters you can control more. But the good thing about these procedures is that if you put a procedure in VHDL in the architecture and not in the process, then it's a concurrent procedure. And a concurrent procedure in VHDL works exactly the same way as a process. This is an excellent way of getting reuse for processes. So once you instantiate that in your architecture, you have your clock generator process. Then, of course, you want to make your test sequencer. And I'm just going to show you an example of that. And the first thing I think we should always do in a test sequencer is to write a log message to the transcript. So you can see that when you start the simulation, something is happening. It's not just stalling for some strange reason. In this case, this log command has an additional parameter, this ID log header, that is used for verbosity control. And it's also, in this case, also used for the layout. So this will give a log header layout view in the, appearance in the transcript. And by the way, this is going both to transcript and to a log file. Then, of course, one of the things you want to do all the time for your test bench is to check values. So in this case, we're checking that the interrupt to the CPU is 0. And then there's a message as a third parameter here. In UVVM, we have made these messages mandatory. We discussed that a lot, but we decided that we wanted to provide a good methodology. And a good methodology is to provide a message like this that explains what this thing is doing when you look at the code, and of course explains it even more when you look at a transcript. Of course, you can skip this message by just writing an empty string, but basically what you're saying then is that if you don't understand this command, you're quite stupid, and that's not a good thing. So I think giving a good message for almost all the commands you're writing is a good thing. For a test bench like this, you very often want to check for stability as well. So for instance, in this case, you want to check that the interrupt to the CPU hasn't had any spikes or been active for a single clock cycle or something before it should go active. So you can check that with the check stable command. You're checking that the interrupt to the CPU has been stable from now back to the reset time. That means you set a timestamp for instance, in this case, at the reset time. And then, of course, you get a positive acknowledge on that as well. Since this is an interrupt controller, you want to generate pulses on the interrupt. In this case, on interrupt source 3, you're setting that to 1 for 1 clock period. And again, you get the transcript of that below. One extremely important thing when making a test bench is to never wait for anything at all unless you have a timeout. You must always have a timeout. So in this case, we have provided a feature for that, a procedure for that, and a wait value. It could also be an await change. In this case, it's an await value, waiting for interrupt to the CPU to go to 1 at the earliest after 0 nanoseconds, at the latest after 2 clock period. That means if it doesn't happen within this time span, it will create or assert an error in your simulation. Also want to show you one of the BFMs. This in this case, it's a simple SPI write. As again, this SPI is a simple bus interface. It's really a dead simple thing with a single cycle and really extremely simple access. Could also have been an Axial Light, Avalon write or whatever. So the first parameter is then the address, then you have the data, and again you have a message, and you can see the result below. So this is a simplified transcript. We also could have a prefix here, message ID and scope shown in the transcript. Just simplify that to make it easier to see in this presentation. It's important to know that all the procedures here have a positive acknowledge if wanted, as shown here. But of course, when you're running this, the complete test suite as a regression test or whatever, you don't want to see all these check values in your transcript, because that would most probably mean thousands, maybe 100,000 of lines. So you want to remove those, filter those out with verbosity control. There's also alert messages and mismatch reports if you don't get the expected result. And of course, means to count the alerts and control how to handle them. This shows you a list of some other commands that are available within the utility library for simple and advanced test benches. So you can see there's clock generators, generate pulse, there's semaphores like flags and barriers, verbosity control, and lots of other stuff. And if you go into the documentation of UVVM, by the way, if you go into the GitHub, you will see on the right-hand side in the GitHub repo for UVVM, there's a link to github.io, and there you'll find an HTML description of the complete behavior and examples and so on of UVVM. So let's go to randomization. In what we call the old UVM, that's from a few years ago, we have what we call basic randomization. And I'm not going to talk about all these examples here. I'm just going to mention one in bold, where you see that you can generate a random integer between 4 and 245 in a very simple way. And this old way of doing things is still the simplest possible solution for simple randomization. But a few years ago, 3 years ago, we improved the randomization capabilities of UVVM. So we added quite a lot of functionality, and it is of course well integrated with UVVM alert handling and logging, for instance. In UVVM, we have a strong focus on overview and readability, as I talked about initially. So we want to add keywords to ease the understanding when it is not obvious how to interpret the parameters, for instance. So if you look at the single method approach, that's a standard approach for this advanced randomization, then if you have simple randomization, it's always easy to understand. This is using protected types, by the way, in VHDL. Not everybody has used that, but if you haven't used that, I would say it's really dead simple to use. You just referring to the protected type called, in this case, a my address, which is a variable, And then that has lots of methods or procedures, in this case, a RAND procedure. And it's easy to understand what this RAND procedure does. It provides an integer between 0 and 18. That's pretty obvious. But what would this mean? A RAND with lots of additional parameters. That is not so obvious. So more complex randomization is definitely more difficult to understand. But there are ways to improve this. So for instance, in UVVM, we add enumerated to make it easier to understand this. So in this case, it's really easy to understand that in this case, you generate a random between 0 and 18, excluding the number of 7. So easy to understand. Or if you want to add a couple of numbers like 13, 31, you can use the add as in this case. In these two cases, the excl and add are not doing anything really. They're just there for readability. But of course, if you want to add something and exclude something, then of course, they also say something about the order here. And it's still simple and easy to understand what's happening here. We're adding some numbers and excluding some numbers to the initial range. We have a similar readability focus for instance, weighting. So in that case, we give the procedure a name like rand val weight. And in that case, the val weight tells you the order of the parameters, i.e. the first one is the value, the second one is the weight. That means a 0 will be created with a weight of 2, 1 with a weight of 3, and 2 with a weight of 5. Same if you have a range with a weight, then in this case you see that the range comes first. So it's the range 0 to 18 with a weight of 4, and the range 19 to 31 with a weight of 1. So it's really easy to understand what's going on here. And then some people tell me, I don't like this. This means there are more characters to write. And yes, there is definitely more characters to write here than compared to not writing them. But that's not understandable for anyone who doesn't know this syntax by heart. So in my opinion, typing code, so not just my opinion, this is by experience, typing code consumes an insignificant part of the total development time. You spend far more time reading and understanding the code over and over again, you and other people reading that code. And that is thus a significant part of the development time. And investing in better code like this yields, I would say, huge return on investment. And it's much, of course, easier to maintain and extend. Let's jump to the next subject, functional coverage. What is that? Well, it's by definition a user-defined metric that measures how much of the design specification has been exercised in verification. So has various functional scenarios been tested? So for instance, the UART has a payload started and ended with both 0 and 1. Has odd and even parity been tested? And with the payload variation above, that would be cross coverage. Has selected cases of baud rate and clock rate been tested. These are just some examples for the UART. This is not like code coverage, where things can be handled for you automatically by the tool. Functional coverage requires a manual process to set up all the wanted scenarios. You have to define these scenarios. That is time consuming, but it's great to check that various specific scenarios have actually been verified. So I'm not going to go into that in detail because that would consume too much time here. I have actually other webinars where you can look at this in more detail. This is just showing you the coverage summary report, so you can see the how useful this is actually. So in this case, we have defined one cover point. It's been given the name, a default name of cover point 1. You can give it your name if you like. And when you report that, you can see all the different bins that you have defined. And contrary to other solutions, where we have seen that there's a problem understanding what coverage actually means, because there's only one number, we have decided to make two numbers for coverage. One which is a bin coverage, and in this case you can see that is 60%. That is because 3 out of 5 bins are fully covered. But we've also provided the hits coverage, and that is a higher number because in addition to the 100% on the 3 bins, you also have some hits on other bins. So I think it's very useful to have both those numbers. Another really useful feature is that with only one single command, without knowing the name of the different cover points, you can report all the coverage in your system. So in this case, you can see for all the different cover points, the statistics for these cover points. We have something called optimized randomization as well. And optimized randomization is randomization without replacement compared to the normal randomization, which is randomization with replacement. So to illustrate that, let's assume you have a bucket of red and blue balls. In this case, you have a probability of 40% of picking a blue ball. If you pick out one of those balls and leave it out of the bucket, there's a 25% probability of now picking a blue ball. That is randomization without replacement. If you had randomization with replacement, the second time around, the blue ball would have been put back into the bucket and it would still have been 40%. This is weighted according to target distribution and, of course, previous events. So let's assume that we have a protocol payload between 0 and 256 bytes. We can define these or define the edge cases for this protocol. So edge cases here would typically be a payload of 0, payload of 1 byte, and the maximum are next to maximum numbers. And in this case, for instance, we say that we want to have 3 occurrences of a payload with 0 bytes, 2 occurrences with a payload of 1 byte, 10 occurrences of 2 to 254 bytes, and so on and so on. And with optimized randomization, that will yield the lowest number of randomizations for a given target. It will give exactly those numbers. And that is a major reduction in number of packets and simulation time. If you would compare this, for instance, to normal randomization, that would have resulted in many thousand packets having to be sent in order to achieve your coverage goals, if you just generate this randomly. Let's jump to the next subject, specification coverage. That, in my opinion, is even more important than functional coverage. This assures that all the requirements have been verified. And in a normal test design for an FPGA, you will specify all the requirements first. So this is just showing 4 different requirements for simplicity. This is a motor control where you have requirement to the acceleration, to the top speed, to the deceleration, and the final position. Of course, you would also have lots of other requirements, but this is just to simplify the scenario. Then you want to report coverage from the test sequencer or test sequencers. After that, you want to generate a summary report. And that summary report should include coverage per requirement, test cases covering each requirement, and requirements covered by each test case. This is what's called requirements traceability matrix. And by the way, this of course could be accumulated over multiple test cases. This is mandatory for safety applications and mission critical application, and it's strictly required by, for instance, ESA. I would say it's also strongly recommended for any good quality assurance. There are expensive tools existing, but UVVM provides this for free and open source. There are also solutions, open source solutions existing to report that a test case, a single test case, has finished successfully. But that is not sufficient. So if you look at this scenario, I'll explain you why. Because what if multiple requirements could be covered by the same test case, as in this case? Well, we could have the approach that is used by some tools, where you make one single test case for every single requirement. But that means for these 4 requirements, you would need to run 4 different test cases. Then you will get result of those test cases and accumulate results of multiple test cases. That's one way of doing it. But of course, this is again 4 test cases, and already with 4 test cases, this is consuming a lot of both development time and CPU time. Whereas what we could do, because these requirements could be checked in sequence, is to first check requirement 1, then requirement 2, and so on and so on. And of course, if you compare this with a system with 100 requirements, maybe you cannot cover all those requirements with 1 test case, but assuming you can cover those with 10 test cases rather than 100 test cases, you've saved a lot of time. And again, it generates various types of reports, as I just mentioned, and accumulate that over multiple test cases. And I should also mention that I think this was one of the things that we developed with ESA, where ESA really had a strong opinion on how this should be. So let's look at an example here with Axis Stream, just to get slightly more concrete here. And let's look at the BFM, a bus functional based test bench first. Let's assume we have a FIFO device in the test with an Axis Stream slave on one side and a master on the other side. And we have clock generator, of course. And then we have our test sequencer using BFMs. And BFMs in the UVVM world are procedures. It's procedure-based. They are dead simple to use. So they are sequential procedures running in this test sequencer pmain, or another test sequencer. And if you look at the result of that, could be interesting. If we do an Axis Stream transmit, we can have a byte array as one of the parameters, and then you can immediately see the result of that. By the way, this ID BFM is the ID you can use for verbosity control to make sure that you turn this message on or off. And you can see that at a given time, the Axis Stream transmit, in this case, of 3B only 1 single byte, and it's done. And then you can have an Axis Stream expect or receive. In this case, an expect. So with expect, you expect it to meet or to match the expected array. And in this case, you get the result of that as well. And we can add more info for debugging, which could be really interesting. So what you can see here is that we have initiated or enabled lots of more verbosity control by using this enable log message on these different IDs. And by doing that, these messages will be written into the transcript and into the log. And in this case, you can see then that you can see when the packet was initiated, when the data was received, and when the packet was completed. You can also, for these BFMs, utilize model protocol, use more of these other signals. You can define different widths for all these signals as well. You can also configure the behavior, like setting maximum wait cycle, set to match data exact or use standard match. You can set the byte endedness, for instance. I can also use this to deassert t-valid some cycles and also deassert t-ready some cycles. And this could be done either randomly or fixed. That means you can have a direct control, or you can just set it up to do this in a random manner. And this random deassertion of t-valid and t-ready have actually enabled lots of bug detection in users' access stream interfaces. This is just showing some of the configuration you can do when it comes to controlling this deassertion of valid and ready. So you can see the word number, duration, probability, and so on. But what if you need to check the device in the test for simultaneous activity? So we have action both on the input side and on the output side at the same time. That will affect the core functionality in between. So for a BFM test bench, we talked about that. We just control that with straightforward procedures. And these are great for simple test benches. They are dedicated procedures in a simple package. You just reference them and call them from a process. But the problem is that the process can only do one thing at a time. So it can either execute that BFM or execute another BFM or do something else. It cannot do multiple things. To do more than one thing, we need multiple threads. And a thread in VHDL would be multiple processes or entities. So you can add those processes here to handle the interface, to handle the access from the test sequencer, to handle some protocol checking and so on, and also to handle more interfacing towards the test sequencer. But for that, we need some kind of inter-process communication, and that is really complex. And it tends to lead to chaos, as it does for design when you have multiple processes that needs to talk to each other. So in this case, we need to have an entity with multiple processes inside and organized in a structured way. This entity, of course, the component in VHDL, is very often called a verification component. We call them VHDL verification components, VVCs. Same thing. And for that, we need a defined protocol. And then we just put all of that into verification components in a structured manner. So let's look at how this can be done in a structured manner. This is showing an example with a simple bus interface. And this is expanding the view here. It contains an interpreter, a command queue, and an executor. The interpreter will look at the command from the test case sequencer and look, is this command for me? If so, I'll put it on the command queue if it is to be queued. Otherwise, if it's a so-called immediate command, I will handle it there and case on what to do. Could be, for instance, to flush the queue or terminate a command or something. If a command has been entered the command queue, the executor will see that, it'll fetch it from the queue, it'll case on what to do, and for the SBI, that would typically be a write, read, or a check. Could also be more complex stuff, but that would be the default. And then call the relevant BFM and execute a transaction towards the device under test. So if you look at that, a VVC-based test bench, how that looks. First, we have the BFM test bench below. And then if you look at the VVC-based test bench above, the difference is that we include these verification components directly on the interfaces of the device under test. Could, of course, also include one for clock generation. And then we have the test sequencer again, but in this case, it's not calling a procedure to handle the BFM, because if it does that, it's blocking the test sequencer. What it does is to send or distribute these commands to the relevant verification component, the target verification component. That means you have to add one more parameter, which is the target verification component, maybe also the instance number. This is connected globally. So the connection between the test sequencer and with these commands, they are connected globally to the verification components with global signals. And that allows us to change the test harness, the test hierarchy exactly as we want without actually making any changes to signals going between the different parts of the hierarchy, because they are connected via global signals. So AVC is really easy to extend and modify. We have this base architecture here, and once we have a base architecture within an entity like this, it's easy to add local sequencers. So could, for instance, add a sequencer to do, for instance, transmit 100 random data. That's quite simple to do. To add that, we can add checkers and monitors inside the verification component and just enable those either with commands or with a configuration of the verification component. And these checkers are far better handled as parallel processes. With this architecture, it's also easy to handle split transactions. So for instance, towards an Avalon or an AXI interface. So in this case, it's an Avalon interface. The first executor here will receive the command and execute a read request towards the device in the test. It will forward the command to the next queue, and the response executor will wait for the response from the device in the test and then execute the read response BFM. This means it's handled in a very structured manner rather than what it's normally in most test benches, where it's creating chaos. It's also easy to handle out of order execution by just having a queue rather than a FIFO in front of the response executor. And as I said, multi-thread interface handling is better controlled as a pipeline. So this allows the overview to be kept for something that normally creates chaos. So what are the advantages of these verification components? Well, we can handle simultaneous activity on multiple interfaces. I said that the test sequencer can distribute the commands to the verification components. It can do that in 0 time using on the delta cycles. That means it can go on to the next interface and handle all of these interfaces simultaneously. Everything is encapsulated, so it allows far better reuse. You can queue stuff, which means you can initiate multiple high-level commands. You can have local sequencers. And what is really unique to UVVM is that it can control all these verification components from a single sequencer. And you can also insert delay between the commands from the sequencer, and that way you can target cycle-related corner cases by skewing one interface with respect to another interface. As I said, simple handling of split transaction out of order, common commands to control UC behavior, simple synchronization of interface actions, and there's also broadcast and multicast possibility here. This all results in a better overview, better maintenance, better extensibility, and better reuse. And this is only possible due to the VVC architecture and a test bench architecture. So some people ask me, these verification components, are they not too advanced? Is this not too much? Well, advanced functionality is great when needed, but what if not? Well, if using an existing verification component, you can just ignore it. Just use it out of the box and don't bother about the extras. And if you make your own verification components using our VVC generator, well, just don't include the advanced stuff. That's an option when you generate that VVC. So if you don't want scoreboard, transaction info, and so on, remove it. If you don't want the checkers, well, remove them. And if you don't need the split transaction capabilities, remove that as well. But by all means, do not remove that if you have split transaction. So we should have, as I said, simplicity where it's needed the most. That's important. But we cannot have simplicity everywhere where the device in the test has some complex verification challenges. So this is a scenario I have. And in my opinion, there are 3 sort of main areas where we spend time. It's to make the test bench with the harness, to make the verification component, and to make the different test sequencers that are going to verify your requirements. If you look at the total workload as percentages for various scenarios for different projects. Then what we see is that for project A here, that's a typical project where you want to make your own verification components. So you need to spend some time to make those. And also building a complex test bench harness. But even in this project A, you're again going to spend so much more time on the test sequencers. That is where you're going to spend almost all your time. And for the other examples here, it's going to be even more time on the test sequencers. So that's the most important thing to simplify. It's by far the most time consuming, and this we really need to simplify as much as possible for the users. That also means that if we don't invest in a good architecture and don't invest in good verification components, the test sequencer time may actually increase a lot. There are lots of free BFMs, post functional models, and verification components with UVVM. And these verification components include lots of different functionality, as I just talked about, and it's the largest collection of VHDL interface models available. This is a list of all the verification components available, and they're all free, they're all open source, they're well documented. And they also have example test benches. And by the way, I should mention that if you go into the UVVM repository, you'll only find the demo test benches. In order to find example test benches, or actually that would be the maintenance test benches that we use, you have to go into the UVVM supplementary repository. So if we look at advanced scoreboard-based test bench, i.e. taking this one step further, this is the test bench we just talked about with verification components for the AXI or the FIFO. So if you want to use a scoreboard-based approach, then we need to add a scoreboard. And that's the simple instantiation in VHDL for UVM, the UVM scoreboard. And again, we would do an AXI stream transmit from the test sequencer, allowing the AXI stream verification component to provide data into the device in the test. And we would tell the AXI stream receiver to receive an AXI stream, not check it in this case. We don't do an AXI stream expect here, just to receive. And then when the data is sent from the AXI stream into the device in the test, the device in the test model can fetch the transaction from the AXI stream master VVC and then provide the expected result into the AXI stream scoreboard. And then when the result goes into the receiver, then that result could also be put into the scoreboard, and then we will match the actual data with the expected data, and the scoreboard will give you a message whether this has been okay or scream out loud if something has gone wrong. And this, if you have a model and scoreboard, that allows functionality to be removed from the test sequencer, which simplifies both the overview and the test sequencer. So, in my opinion, as I said before, a good architecture allows better understanding at all levels. And what we try to do is to standardize the way the verification components should be made so that all the verification components work the same way. And that also allows the test bench to be made the same way and for the users to apply verification components the same way everywhere within a UVM environment. So, yes, I said, allows simplification. Users know how verification components behave, how any test harness will work, and verification components from different users will work together. Let's look at the full picture. We have a device in the test, in this case, an Ethernet switch. Again, we have some verification components that we connect to that. And for an Ethernet switch, it's much better to use verification components than BFM because you're going to have simultaneous activity on multiple interfaces. In this case, we have an SPI verification component, a UART, a GMI and an SPI verification component. And in this case, the SPI will provide data to the Ethernet module inside. And the GMI, of course, is the physical interface of the Ethernet on the other side. Then we can connect the scoreboards to these verification components to make sure that we check the data out of these verification components in a very structured manner. Then we can have a model, and we can have a UART monitor just to check what's actually going from the UART into the Ethernet switch, the device in the test. We could have a watchdog timer, an activity watchdog. We could also have what we call hierarchical verification components. And that is something we need for Ethernet because Ethernet doesn't have a physical interface. It's going to use one of the other verification components in this case, or one of the other interfaces as their physical interface to the device in the test. In this case, the SPI on one side and the GMI on the other side. And the good thing about having an Ethernet verification component is that the test sequencer can write Ethernet commands rather than writing lots and lots of GMI or SPI commands. And of course, once we have an Ethernet verification components, it makes sense also to have an Ethernet scoreboard, because that way the scoreboard will tell you about packet matches rather than the GMI or SPI scoreboards telling you about word mismatches. You can also have an error injector in there and lots of other stuff. So the question again, is this too much? Are there too many verification IP components here? Is it too much structure? Well, VVCs are needed to check multiple interfaces. We should not go back to BFMs for this. But what if we decide to simplify this and remove everything else? What happens then? If we want to have the same verification requirements coverage, of course, and the same quality. But what happens is if we do this is that we have to put the same functionality somewhere else. And that some of that would go into the test sequencer, but very unstructured. It would also be going into lots of support procedures, giving you far less overview, and it definitely not maintainable, not very reusable at all. So this will be the result of that if you go for the same quality that you would have for the previous system. And debugging is much easier also with a good architecture. According to Wilson Research, on average, an FPGA project, you spend half the time on verification. And half the time of that, again, is spent on debugging. I think that that can be improved a lot. So let's talk about improving verification in general. It's all about the things I talked about previously: overview, modifiability, debuggability, and reusability, and awareness about how this affects the time and quality. We need to allow time upfront to structure, as we do for design. We should discuss the test bench architecture before coding with a sparring partner. We should have a walkthrough on that before we start coding it. And the same applies to control and status of all stimuli and checkers. Also, how to reach corner cases, which could be really complex, both value and cycle related with functional coverage, and the cycle, value related with functional coverage, and the cycle related by skewing these interfaces with respect to each other. So you want to do divide and conquer at all stages. And even more important, prioritize the reader at all times. So, as I said, half the verification time is spent on debugging, and this gives us a huge improvement potential if we do things in a proper and a good way. If we assume a 6,000 hour project, that means approximately 3,000 hours on verification. And if we can save this much time on debugging, test planning, test bench development, and creating a running simulation, we can actually save 1,500 hours, which is a 50% improvement in this case. And from what I've seen in lots of projects, this is actually realistic. depending, of course, totally on where you are today, how mature you are with respect to verification and a good structure. As I said, we do courses, one on advanced VHDL verification and another one on design. The courses are explained and described on our website, so you can just check it out there. And the next courses will be in November. We're currently doing a new ESA UVM extension project, started up in March, and the first new functionality was published in July. And these are: 1, detection of unexpected or unwanted transactions on interfaces. That hasn't been available before. So previously, if a UART, for instance, was transmitting something out on the TX interface, you would want to check that by writing a BFM or verification component command to expect some data or receive some data on that interface. But what if you didn't expect any action on that interface? Then there wasn't anything in the previous system that would check for that. So you would have had to check that yourself, and I think most designers, verification engineers never did that. So that means if their device in the test was sending out some garbage when it shouldn't do that, it probably wouldn't be detected. So now we included detection of unexpected, unwanted transactions on all the interfaces. That also means that it's not backwards compatible if you have problems, if you have a device in the test that isn't behaving properly, but you will then detect that. We also included completion detection. We did have completion detection on verification components before, using a broadcast, for instance, on completion, await completion. We now also introduced completion detection on all the different scoreboards. So that means you can either check for completion or wait for the scoreboards to complete, so that you know that when you finish your test bench, all verification components have finished what they should do. There's nothing in the queue, there's nothing in the executors, then there's nothing in the scoreboards. That's important to make sure that you are actually checking the right thing. So, UVM in a nutshell. I think there's a huge improvement potential for more structured FPGA verification. And we talked about that. UVM targets all of this and has been a game changer for efficiency and quality. As I said, it's free, it's open source, both the utility library, the verification component system, all the BFMs and specification coverage, verification components, and so on and so on. And it has also great documentation. It has the largest collection of interface models. I mentioned that. We work tightly with ESA, and we also do webinars for Siemens, for Aldec, and so on. And we tested out, as I said, with the different simulators, Questa, Model Sim, Rivera Pro, GHDL, and NVC. All of this has resulted in the usage exploding. As I said today, between 35 and 40% of all VHDL FPGA designers worldwide are using UVM today. And you can save a lot of man hours and calendar time on a medium complex project, of course, even more on a really complex project, and at the same time, improve time to market, mean time between failure, and life cycle cost. And that's it. Thank you. Any questions?
Yeah, thank you, Espen. It's appreciated.
No, any questions? No questions. Everything was crystal
Yes.
clear.
Yeah, thank you. Thank you, Espen.
Okay, right. Thank you. Bye.